Hey, this is Dr. B, and let's talk a little bit more about free energy. This is a formula that was developed by Josiah Willard Gibbs in the 19th century at Yale University in New Haven, Connecticut, and I live about 10 miles from there. Okay. It states that if you want to figure out if a process is spontaneous, just figure out if this delta G value is negative. It comes from the change in enthalpy, where an exothermic process, as you might predict, is typically spontaneous, but you also have to consider whether it's becoming more random. If it is becoming more random, that will favor a spontaneous process, especially if the temperature is high. Be aware, however, that these values are oftentimes in the kilojoule values, whereas the entropy values are oftentimes in the joule values, meaning this is a big-time player, this is a small-time player. Knowing that, we can oftentimes predict whether a process will be spontaneous or not without even knowing the values, right? We just need to know whether they're positive or negative. I'll consider this in each case from the point of view that a spontaneous reaction is a good reaction. That helps me. Okay, this is not good, right? It's endothermic. That's not, and that's the big time player. So this is probably non-spontaneous. However, it is getting more random. So I would say it's usually non-spontaneous, but if the temperature is high enough and and this is a big value, maybe it can overcome it. Reaction proceeds spontaneously at high temperatures. At low temperatures, the reaction will go so if you get high enough, see, here's what they're saying. If you get high enough, this value can overcome the enthalpy. Maybe, right? But at low temperatures, it goes in the opposite direction. You know, this opposite direction stuff is like cute, but I think the point is that you're probably going to need a very high temperature to overcome the large non-spontaneous enthalpy factor. It's endothermic. Okay, next one. Yeah, that's bad, right? It's endothermic. This is bad too. If this is bad and this is bad, it doesn't matter. It's non-spontaneous, period, right? The reaction is spontaneous in the reverse direction. Don't do that. It's non-spontaneous in the forward direction at all temperatures. How about this one? That is good, and that is good. So it doesn't matter what their values is. That reaction will be spontaneous no matter what. Reaction spontaneous. Yay, they finally did it in the forward direction. Thank you. Okay, here it is looking spontaneous because it's exothermic, but it's getting more organized. So I would say that this is going to be almost always spontaneous, and this value could kick in to make it non-spontaneous if you heat it up enough. Reactions proceed spontaneously at low temperatures. At high temperatures, it might make it non-spontaneous as you increase the temperature. Okay, that's a look at the values. Let's consider a chemical reaction here. We're taking some chalk and we're decomposing it. The change in the free energy at room temperature is positive. It's non-spontaneous. But when you hit 835, it becomes spontaneous. So consider what will happen to the partial pressure of carbon dioxide. That's product at over a temperature range. You're asked to fill in this graph. Think about it for a second. Tell me what you'd do. I would say that it's going to start to kick in somewhere at around 835. Right? There you go. And if you had to explain it, it's nice to include the word equilibrium when you explain it. Don't forget, equilibrium is zero. When delta G is zero, you're in a state of equilibrium. So you get a favorable equilibrium beyond 835. Okay, that's a little bit more about Gibbs free energy.